Let's outline how to solve rational inequalities. So here's a how-to guide on how to solve an inequality that looks like p of x divided by q of x is bigger than or equal to 0. P and q are polynomials, so this is a rational function. The first step is you just find where p of x equals 0 and where q of x is equal to 0. These are the places where the sign of this rational function could possibly change from positive to negative or vice versa. Then you place these values on a number line. These values create barriers where the sign can change. And then the last step is you simply test values in each region. So let's see examples of this procedure. How about if I tried to solve x squared minus 5x minus 14 all over x squared minus 9 is less than or equal to 0. So the first step is to find where the top and the bottom functions are equal to 0. So I'm finding the zeros of the function and the vertical asymptotes. Well, this is the function if you factor the top, x minus 7 times x plus 2 divided by, and then the bottom you may notice a difference of squares. So I have x plus 3 times x minus 3. So it's fairly easy to identify where the zeros are and the vertical asymptotes are. I'm going to plot those values on a number line. So I have negative 3, negative 2. Those are different values here. I have also 3 and 7. This creates barriers that section the number line into regions. I'm going to just test each region to see if the function is positive or negative. So if I plug in a very negative number, so if I plug in negative 4, negative 5, or a very big negative number, then you could do the calculation and I think you'll find a positive result. If you plug in a number into this function between negative 2 and negative 3, like negative 2.5, you'll get a negative. Plugging in 0 is pretty easy to check in this region. So if I plug in 0, I get negative 14 divided by negative 9, which is positive. You can plug in 4 or 5 to get a negative number, and then you can plug in a very, very big number to get a positive. If you plug in a very big number, x squared is positive on the bottom, x squared is positive on the top. The smaller terms don't affect things for large values of x as much as the x squared does. So anyway, this is positive. My answer is negative 3 up to negative 2. That's the first place where I find a negative. And additionally, between 3 and 7. Notice I put a soft parentheses on the bottom here because negative 3 is a vertical asymptote. It's not actually in the domain of the function, but negative 2 is. Same thing with 3 and 7. So that's the basic process. Let's do a couple more examples. How about if I do 2 minus x plus 1 over x is less than 0. Now the first step, even before I do step 1 listed here, is to write the function in the correct form. So far it's not. It's in a form that you may find after doing long division, but I'd prefer the form that looks like this. So in order to get that form, I'm first going to multiply by a common denominator. So I'm going to have 2 minus x times x over x plus 1 over x. So I can add and I can find 2x minus x squared plus 1 all over x. I want to find where that's less than 0. Well, now I can follow through this process. X equals 0 is where the bottom is 0. The top, I can use the quadratic formula. And if I use the quadratic formula, I find x can equal 1 plus or minus the square root of 2. So those give me my values for my number line. So I have 0 is one value that creates a barrier. 1 minus root 2 is another number. That's about negative 0.41. The other value is 1 plus root 2, which is approximately 2.41. Okay, so I have my regions sectioned off. I test different values. If you test a positive value, that's like, say, plugging in 1. So in this region, if I plug in 1, I get 2 minus 1 plus 1. So that's a positive. You could test the other regions, plugging in a very negative number. I think you'll get a positive in this region. If you plug a value in here, I think you'll get a negative. And lastly, you will get a negative in this region. So in the problem, I'm asking to find where the negative regions are. So my solution, I can write an interval notation. It can be everything up to 1 minus root 2 going to 0, and everything between, including 1 plus root 2 on. Let's finish this video with one final example. How about if I do x plus 1 plus 4 over x minus 3? Again, I need to write my function in this form in order to do my process. So actually, let's find when that's positive. So this is adding the fractions. You could do the algebra on your own if you'd like, but I believe you will find x minus 1 squared over x minus 3. And you want to find where that's positive. So my number line contains 1 and 3. 1 is the 0 of the function of multiplicity 2, and 3 is a vertical asymptote. Those are the places where this rational function can possibly change sign. Then when you plot or plug in different values, for example, if you plug in 0, 2, and 4, you'll get a negative in this region, a negative in this region, and a positive in this region. I wanted to do this example to show you that the signs don't always flip-flop from positive to negative, especially if you have a root of even multiplicity. If you remember the graph of the rational function, that's where this graph of the function just kisses the x-axis and goes back up, not crossing through. So the sign actually doesn't change because of that. Regardless, my solution is all numbers 3 on. Okay, wonderful.